Hello, Stefan. Hello, Jason. We'll give everybody just a minute or two to file in, whoever wants to see. Hey, Rob, how you doing tonight? Audio sound good? Cool. It just, for some reason, we got a huge delay tonight. I don't know why. It's like 30 seconds almost. I tried to up the resolution too and do this in high def with widescreen. Does the image look okay? Good evening, Omega. Awesome. I've been, our internet service provider just got bought out again, and I've been all over them to try to fix my link a little bit better. I don't know if it's better or not. It's not the chat end. The chat end is instant. It's the feed end. So the video is lagging by about 30 seconds tonight. I was just experimenting a little bit on the preview, and it's about 30 seconds. I don't know why, because all of my PC settings are set for no buffer, and I don't see any buffer on the preview screens here. But by the time it makes it up to YouTube and then comes back down, it seems that there's a delay. We'll just give another minute or two and we'll get rolling here. Good evening, Josh. How are you tonight? Yeah, no problem, Jason. I figured I would do this one live, just because I'm going to get really, really deep into it. And I figured if I do this one live, A, it's going to save me having to edit it. And then B, if I don't explain something clearly, you can stop me right there, or you can stop me 30 seconds later with the delay, and then we can dive into it a little bit deeper. Oh, cool. Thanks, Stefan. Yeah, trying to explain electricity is tough because you can't see it, and when it's something you can't see, it's hard to teach. So, okay, let's get started with tonight's topic. So, as everybody knows that watches the channel, I purchased a bunch of parts off of eBay to start getting a probe system together for the Fpga. And we're using Renishaw hardware. It's all older style hardware, so it's all used off of eBay. And I got the main pieces, but I've been having trouble finding the ancillary pieces, mainly the machine interface pieces. And the prices on them are just insanely high. They want like $500–600 so far on eBay for an MI12, and then like $150–200 for an MI8-4. So, you know, I'm going to use what I've got and then piece together the rest because A, I like doing it, and B, I want to save myself $500 because I got stuff laying on the shelf that with a little bit of effort can do the job for me. So that's where we are tonight. So what I did is I have everything up and running and working, so we'll demo that, and then we'll go in and I'll kind of explain how the Renishaw hardware is working and functioning from what I was able to ascertain. So first, let's review what the system is. So you have a probe, it goes in the spindle, and it uses infrared light to transmit to a receiver. So this is the receiver that I chose to use. It's a little bit older version. It's called an OMM, or optical module machine, whatever you want to call it. And these are actually still relevant and sold today. And the newer probes have a really cool system where you can program a new probe into a legacy mode, they call it, and you can still use an original OMM, MI12, MI8 to, you know, interface with the machine, but then you can use a newer probe. So if you break your probe and you can't find an older one, the newer ones are still backwards compatible. So kudos to Renishaw. They really do make good stuff. And I'll go through some of the stuff and why I like, you know, the OMM. You know, I have it all apart on the bench. So you start with a probe, and that's in the spindle. It's got an infrared transmitter on it, and then you need an OMM, and this has the infrared receiver on it, and then this is a wired connection. Now after the OMM, you need another box, and that box is called an MI12. Now what the MI12 does is it receives signals from the OMM, and then it outputs some dry contacts, and it inputs a couple of switches to turn the probe on and off, and then to tell the machine whether or not the probe has been triggered or not. Now if you have a tool setter, the tool setters are actually pretty easy. They're just dry contacts. So there's another interface for a tool setter, and that's called the MI8-4. So it starts at the OMM, it goes to the MI12, and then it goes to the MI8, and then it goes to the machine if you have a tool setter and a spindle probe. So what we're going to talk about tonight, we're going to talk about how the OMM works, and then we're going to talk about the signals used to communicate from the OMM to the MI12, and then also just briefly touch on what the MI8-4 does. So that's going to be tonight's topic. So let me just show you what I've got on the bench real quick. So this is our workbench setup that we've got, and here is the circuit board out of the OMM. I'll take the cover off of it. Okay, so that's the circuit board from the OMM, and then this big honking piece of hardware up at the top is a commercial piece of product made by National Instruments. If you've watched some of my videos and streams before, you know that I'm a National Instruments guy. I do a lot of Labview and hardware integration. So this thing has a lot of horsepower in it that will allow us to decode the signals coming off of the OMM circuit board exactly the same way as Renishaw's MI12 does. So what I'm doing here is I'm figuring out how this works using this stuff for now, and then maybe in the future I'll replace this stuff with like a PIC chip or something else. We'll see moving forward. This might be in the machine a while. I already have one of these in the machine. I just got to put these modules in it. And I'll go into detail on exactly what's going on here. Real quick though, let's just talk about how to take this thing apart. So this is the housing for it, and this is a pretty nice housing. I mean, this is machined out of a piece of billet aluminum, and then the little plastic pads you got in here, those are just like little spring clips, and there's holes in the circuit board that retain the board in the housing. And then you've got your wires that connect to the board. They're on little screw terminals on the board. And then to seal it and close it, you've got this cap that's got your sight window for the infrared to pass through. And then it also has an O-ring here. And then if you look carefully at it, with these lined up with these wrench flats, there's two little nicks in there. They're kind of hard to see on camera. But that's for a spanner wrench so that you can unscrew this part, and that's what holds the glass in. And this is real glass. It's not plastic. So to take this apart, there's actually 4 holes here, and there's 4 screws, but only 2 screws hold it together. So you'll note when you take this apart, you'll notice that 2 of the screws are really short, and then 2 of the screws are really long. So you can use the screws as jack screws to take this thing apart. So what you do is you take out the short little screws and you put the long screws in the holes where the short little screws were, and then you tighten it down, and it will slowly jack the cover off, because the O-ring seal on this thing is pretty good. Okay? So that's how you take this apart, and then you'll see the circuit board sitting in there. Now again, Renishaw does an excellent job at making these things maintainable and useful. So this little wire here, okay, this is actually a handle so that you can extract the circuit board easily. So this is normally tucked in down, so you just fold it up and then pull, and you can pop the circuit board right out. So, you know, they thought of maintenance. It's machined well. It's built well. You know, it's a nice piece of hardware. Now, the circuit board is designed pretty well also. So, you know, that's the system here. Now, I also have the probe sitting over here as well. So this is a MP10 probe, and we'll interface the probe with the OMM. And then we've got the OMM wired up here to this box to get the data off of it. And then from here, this will be wired to the machine to get the signals into the machine. So from there, let's look at the wiring real quick. So if we go from the OMM to the MI12, the wiring is on page 21 of the manual. So here is the wiring schematic to go from the OMM. So the MI12 can handle 2 OMMs. So if you have a larger machine, you can put 1 OMM on each side to give you good optical coverage if you have areas where the probe is dropping out. So we can handle 2 OMMs with this. With the hardware I'm using, I could handle 8 of them. You know, this hardware is such high horsepower, this is not a problem. So you've got all these wires coming off the OMM. There's 5 of them. You've got signal and not signal. Now that's the yellow and gray wire. Now what those are is that's actually an RS-422 signal. So what it does is each one of these lines goes from 0 to 5 volts, alternating back and forth. So when this one's 0, this one's 5 volts. When this one's 0, this one's 5 volts. And what it does is it gives you a differential digital line that's very noise immune, and it can transmit high-speed signals long distances. So that's why they're using this. Then you've got this start line. Now this one gave me a little bit of heartburn. So it only took me about 2 hours to figure this out and to get this working. It took me about another 3 hours to figure this guy out, because they're actually using the start line for two purposes. One, it sends the start signal to turn the probe on and off. And then two, they're also doing double duty with this guy to transmit the signal strength of the probe, or the OMM receiving the probe signal, back to the MI12. And then there's a couple of pads on the MI12 where you can use a voltmeter to see what your signal strength is. And then the other two wires are 10 volts and then ground. They call it 0 volts. And this does operate at 10 volts. The OMM operates at 10 volts. The MI12 supplies that 10 volt regulated voltage to the OMM. So that's how you would normally wire the OMM to the MI12. And then coming out of the MI12, you basically have the probe status coming out here. So then if you have a tool setter in addition to the spindle probe, now you're going to need another box, and that's the MI8. So let's just really briefly touch on the MI8 real quick. That's on page 25. So the MI8 takes the signal from the tool setter probe, which is right here, blue and green, and that goes into A2 and 3. And then A4 and 5 is the inspection system input. So this is the probe signal coming from the MI12. Okay, so you follow me? So you go from OMM, MI12 to this MI8. Then you have this inspection select signal, A7. This comes from the CNC machine. And the machine will tell the MI8, do I want to look at a tool setter? Am I setting tools? Or do I want to look at the spindle probe? Am I setting, work offsets? And then this has the probe status output. So this select pin selects between the tool setter probe input or the OMM MI12 probe input, and then it outputs it accordingly. So this box is pretty simple. It's a pretty dumb box. There's not much going on in here. What's going on in here is all in that MI12. This guy is really the brains of the operation. The OMM is actually pretty stupid. It doesn't have any real hardcore processing in it at all. All it is an optical interface that is then forwarding data to the MI12, and that is where all the data decoding is happening. So if you want to replace the MI12 with something custom, or you don't want to buy an MI12, there was quite a bit of stuff going on in there that you have to duplicate to get all this working. So anybody have any questions, or did I lose anybody so far? I know there's quite a bit of lag, so. Okay, so let's just take a little bit closer look at the hardware that I've got and how I have it wired up. I've got a little handheld camera where I can zoom in on some stuff here. So let's switch over to that one. So there's a up-close shot of the OMM, and then from the OMM we're wired into this National Instruments hardware. Let's see if we can get a shot of this. Okay, so we've got 3 modules here, and that middle module with the green circuit board, that circuit board is just a breakout board so that I can easily wire in the signals. Now there's only one signal going into this board, and that's the RS422 signal line coming from the OMM into this device. So that's how we're actually getting the probe data, is through that middle module. And all it is a high-speed digital input. Okay, so it can read the on-offs from the OMM at a very high speed. The signals coming off the OMM are around a megahertz, so you really need some high-speed stuff to read it. Now this module here on the end, now that one is a digital output module. So that's what we're using to send the start command to the OMM to turn the probe on. Now again, it's not just an on-off signal. This has to be modulated. I found that 2 kilohertz seemed to work the best. And then over here at the other end, we've got one analog input module to read an analog voltage, and then that is going to be reading the signal strength coming from the probe. So that's the setup. So let's see it in action, and we can show it working. So let me pull up the code. So this is the test code that I wrote to verify and check all my software. And right now it's in error mode. And when it's in error mode, I force the touch signal on. That way, if you lose communications with the probe or something happens to the probe, it will trigger the machine to stop moving so you won't crash the machine. Your work offsets are going to be wrong, but typically they're going to be wrong in the correct direction, and you're less likely to crash. There are some instances where stopping it would cause a crash if you let the program go on, but your macros should check for this error signal, and if they see this error signal, you should stop your program so that you don't continue on with bad probe data. So then, to turn the probe on, I just got to angle the circuit board a little bit here so that it kind of points at the probe. We send the start, so we'll send the start, and now the probe turned on. Okay, so now we don't have an error, and the probe is running, and we've got good signal strength. Now if I put my hand between the probe and the OMM, you'll see the signal strength drop. If I take my hand away, you'll see the signal strength go back up. And then we can trigger the probe so we can touch it and we can see when it's touching. Okay? And then there's also a change flag. So anytime the touch line transitions from either touching or not touching, the change flag lights up on the very first edge of transition. Okay? Not a good idea to keep going. Yes, yeah, you wanna stop if you get an error. So that's what this that's what our error indicator here will do for us. It will stop. And if I completely try to cover the probe and we lose all transmissions, it's kind of actually hard to do. There you go. You can see. So now that is simulating a complete blockage of the signal, and it errors instantly. It actually errors within about 20 milliseconds. So it's pretty fast on the error between loss of data and reestablishing of data. Okay, so that's what the error. And I'll go through the code and how this is actually working as we go on. So it's pretty slick. Okay, so let's just look at one other thing that I had to do. If you notice, way over here, I've got the battery cover off of the actual probe itself, and then I've got clip leads on here. So I'm actually powering the probe with an adjustable power supply. And what that allowed me to do is I can lower the voltage artificially to simulate a low battery condition, and that's how we can figure out how the low battery signal works. So it trips at about 5.5 volts. So if I lower this down to 5.5, you'll see the low battery kick on. So it should kick on right about here. Yep. So there's the low battery kick. And then it's got a fair bit of hysteresis to it. So the battery voltage has to return all the way up to about 6 3/4 before the low battery indicator will turn back off. So that's how I was able to figure out and test the low battery indication. So first, let's talk about how the probe is sending data. So these older probes are sending data a little bit archaic. They're not using a very robust methodology for transmitting RF data or IF data, infrared data. If you use a standard, television remote control, what they're doing and how these work is they use a modulated signal. So they don't just turn the infrared transmitter on and off, on for 1, off for 0. What they actually do is they send a burst out at like 40 kilohertz. So a 40 kilohertz burst will represent a 1. Okay? And what that does is if you have a lot of infrared in the room, like direct sunlight shining on the infrared receiver, it will saturate the infrared receiver to the point where it will no longer be able to read correctly. It won't be able to distinguish the on-offs from, background noise. So by having that burst, what you can do is you can put a low-pass filter on the system so that only the high frequency, or the high-pass filter, so only a high-frequency burst comes through, and you get a much more reliable and robust system. Now, all the new probes that Renishaw makes use a modulated signal. So they fixed it. It's just harder to do that, and back when the MP10 probe was designed, it took a lot of electronics to do that burst mode, and there's not a lot of space in these things, so that's probably why they did it. Now the newer probes, the electronics are a lot smaller, it's a lot easier to do today. The newer probes use a modulated burst methodology for transmitting that infrared data, and that's why you have to use legacy mode, which converts them back to the old method and to use a new probe with an older OMM. So now, what is that data that they're sending out? Well, with the old probes, they're just turning the IR transmitter on and off, and then the OMM is receiving that on-off data and then just forwarding it out to the MI12. So that's what we're intercepting here. So our probe turned off, so we got to turn it back on again. So now that it's back on again, that's what this graph is displaying. Okay, so they're sending 8 bits of data with the probe, and the red, I put cursors here at each bit time. Okay, so if you're familiar with asynchronous data transmission, your RS-232 port on your computer, the older style, it sends a asynchronous communication stream. So it synchronizes on the first transition of an edge, which would be out here, and then from there, after it's synchronized with itself, it uses its internal clock to then sample at pre-described times. That's what your baud rate is. Okay, so with knowing your baud rate, the receiving machine will know what these times are to sample the data to then, form the correct data bit. Now, originally I thought, when I saw the RS-422 chips on the boards, originally I thought that I was going to be able to use a standard UART to do this. Unfortunately, I was mistaken. You cannot use a standard RS-422, 485, 232 UART to read this data because it doesn't follow the spec as it should. It's close, but it's not close enough. So normally with the RS-232, 422 specs, what you do is you have one start bit, and then at each bit time you get edge transitions, whether it needs to go high or low, and if it doesn't need to change, it doesn't change until you're done, and then at the end you get one stop bit. So they are not using any stop bits, and then what happens is there's no start bit either. It's just you get an edge transition, and then 2 microseconds later, that's your first data byte, and then after that, it's every period that you get a data byte. And if you notice here, it turns on and off for each bit time. Oh, probe turned off again. So it turns on and off for each bit time. So that is way different than standard RS-232, 422 data transmissions. Okay, and if you also notice with RS-232, 422 transmissions, the data line is held in the correct logic position, either a 1 or a 0, for the entire bit time. So the bit time is going to be 1 over the baud rate, and that will give you how much time that the bit time is. With these, the bit time is only a few microseconds. So the timing requirements to read these are much more stringent than you're going to see on a typical RS-232 line. So you need a much more accurate clock to be able to hit all of these times and read at the correct points. So the hardware I'm using uses a 40 megahertz crystal. I think it's a 100 ppm crystal, so it's a very accurate crystal, so we can read this pretty easily. So for each 8-bit byte, there's a couple of things that go on. First, the first 2 bytes are always 0. And a 0 is represented by the IR light turning on. At least in my mind it is. So every transmission you'll see, the first 2 elements are 0. If they're not 0, that's an error indication. Either you're out of sync, or you got a bad packet, or you're getting noise from somewhere. But for whatever reason, that is an error indication if the first 2 bits are not 0. The next 2 bits are the touch indication. So if I trigger the probe, you'll see one turn off and the next one turn on. So you can see it's toggling back and forth. So then, because these are toggling back and forth, you can do another error check where if you see both of these bits on or both of these bits off, that's another error. Okay, they should always be complement to each other. So that's the next 2 bits. Then the next 2 bits are the changed light. So if I change this a lot real fast, you'll see every once in a while these will toggle and flip. So you can see every once in a while they toggle and flip as it's changed. Now, and again, there's another error check you can do here. If either one of these is both 1 or both 0, that's also an indication of error. Okay? So then the last 2 bits are the low battery flag, and it follows the same paradigm. They swap places. So if I lower the voltage again, so here they'll swap right about now. Yep, there they go. So now this one is 1 and this one is 0. So that is the entire bit packet and all of the data contained in it. So you can see those flopping back and forth. So the data byte is actually pretty easy to decode. The hard part when doing this is getting this timing correct. And this timing, if you see all these numbers over here, what these are ticks of the 40 megahertz clock. So rather than scaling them, we just left them into counts. So to figure that out, we can easily bring a calculator. 40 megahertz. 1 over x is 25 nanoseconds. Save that, and if we take 50 times 25 nanoseconds, what you get is 1.25 microseconds. So our first sampling is going to happen 1.25 microseconds after we see this falling edge. So you can see that the timing on this is really tight. And then after that, it's 321 ticks, which is roughly 8 microseconds. So every 8.025 microseconds, that might be the clock resolution bouncing around. Every 8 microseconds, you want to read one of the bytes. Okay, so that is an equivalent baud rate of 124,610 bits per second. So it's a little bit faster than the fastest serial UART can go, and it's also a non-standard baud rate. So serial UARTs are designed to do 115, 200 as the maximum, and then they double from there. So by being a non-standard baud rate, that's again limiting the ability for you to use a standard UART. Okay, so now the other piece of testing that you want to do is you want to do stability testing on this thing to make sure that you're decoding it correctly the entire time. So let's turn it back on again. And after this data, I've got some more graphs down here at the bottom. So what these graphs are showing is this is a graph of every single byte that's coming off the probe while it's running. So the problem with these indicators up here is these indicators are called lossy in our industry, meaning that you're not guaranteed to see every single transition, every single value. What I did down here is these are lossless. So you are going to see every single value coming off the probe, so you can see little blips. So if you get a blip here, let me autoscale this. If you get a blip here, you'll know that you incorrectly read the probe, because right now it should be stable. It's not being touched. And then if I go to touch it, okay, what you'll see is you'll see the value change, and that indicates the touch flag has turned on, the change flag is turned on, and then the change flag turns off, and it's just a touch, flag. And then when you release, it goes back to the touch flag being off, and the change flag comes back on, then it returns to its stable state. Okay, so you can see, we are stable. We're not getting any erroneous data points in between as this thing runs. And I let this run all day, and it didn't receive any misindications. So it's very stable. Now this bottom graph is displaying the delta time between each transmission. So under normal idle steady state, the probe sends out a data byte every 16.4 milliseconds. So every 16 milliseconds, the probe sends out a burst of information from the IR port that gets received and it gets updated. So that's how you can do your error check. If the probe stops or gets blocked instantly, you just wait. If you don't receive a byte within 20 milliseconds, you can time out and then flag the error, and then the machine will stop. Now, I thought that the probe always sent it out at 16 millisecond increments. And I did some math, and it's like, oh, if you want really good accuracy, you have to have a very low feed rate for that probe to trigger the machine to stop if you have a 16 millisecond wait time. But what happens is as you start triggering the probe, it will interject an extra data byte every time the probe is triggered. So you get instant notification that the probe was triggered by the update rate changing. So that's pretty cool. And that's where I had some bugs at the beginning, because I thought there was an extra stop bit back here at the end, but there isn't. So every once in a while, what would happen is I would lose one of the start bits, and then my data would get out of sync and it would get all messed up. So that's why I did this piece of code. So that's basically it for the operation for the OMM and how it works. And that's the interface between the OMM and the MI12. We can go in a little bit deeper and look at the code and see how this is being done, and we can look at the circuit board a little bit and see how this is being done. Does anybody have any questions? Am I boring you to death, or is this cool stuff? We still have 21 people watching, so must be good. I'm going to make this video public when we're done, so then people can watch it after the fact as well. So let me, I'll show you a little bit of the code under the hood and how we're actually accomplishing it, and what we're doing. And then we'll also talk about the start signal. That was the tricky one. The start one was the trick. So if you're not familiar with National Instruments Labview, no, Josh, no quiz. You can watch the video as many times as you want, but no quiz. So if you're not familiar with National Instruments Labview, this is Labview, and Labview is a graphical programming language. Now, when you first look at it, it kind of looks like Greek. Well, I don't think Greek looks like this either, but it doesn't look very understandable, but it's actually pretty easy to read once you get used to it. So basically all we're doing here is this stuff down here at the bottom is just my diagnostic code. So this first piece here is reading a data stream off of the embedded processor, And the embedded processor that we're using is called an FPGA. It stands for Field Programmable Gate Array. And what you can think of an FPGA as, it's basically a microprocessor that doesn't have any set form. So a standard microprocessor that's in your PC, or like a PIC chip or an Arduino or a Raspberry Pi, they're set in stone of what their form factor is, and basically they just read instructions and process those instructions. On an FPGA, it's malleable. You can form whatever processors you want. So if you need a whole bunch of control loops, you can put a whole bunch of control loops on an FPGA and they'll all run in true parallelism. It's not like a standard processor where it just serializes everything. So this first section basically just reads a data stream, and then a data array comes out. It's just a series of numbers. And then we are doing some manipulation here to split it apart and find the first start bit. And that's how we can display the data packet stable. So that's what this piece of code is doing. It's basically just looking for a large time delay, and then if it sees a large time delay, it knows that the next transition that's coming through is the start, and then it will, take that subset of data and display it on this XY graph for us. So that's what this bottom piece of code is doing. And then this middle section of code, it's doing the same thing, but it's another data array, and that's given the byte and time graphs. Okay, so that's these ones down here. Okay, so this is just diagnostic code. This will not be in the final application. This is just to test and figure out. This little tiny bit of code up here, this is what would be in the final application. And basically it's just reading out the final bits of error, touch, changed, low battery, and signal strength. Okay, and then it allows you to send the start trigger. Okay, so this is the high-level interface. Now from here, what we have to do is we have to look at the piece of code that's running. So let me switch back over to here, just so you kind of have an idea of the lay of the land. The code that we just looked at is running on this guy, and it uses Ethernet to transmit the data to the computer screen. Okay, so the code's running on this guy. Now, in the back of this guy down at the bottom, that's where that FPGA is located, and it's interfaced to all of these modules directly. And then the FPGA is interfaced to this piece. Okay, so looking back at our code here, this is how we interface the data from the FPGA into this floating point processor. This is a standard processor. Okay, so let's look at the code that's running on the FPGA, and then we can kind of see how it is all decoded and runs in the firmware. All right, so this is the FPGA VI, and if you notice, it looks very similar to the code that's running on the fixed point, but it's got a lot more chaff going on in it. We gotta yes, Tim. So these probes are designed to work with any machine, as long as your machine has a dry contact input and a dry contact output, or a syncing sourcing input output. The Renishaw hardware will work for any of them. So yeah, you can use one of these probes on a Tormach. It would work just fine. And you don't have to do any of this. I'm doing this because I'm cheap and I don't want to spend another $500 on an MI12. I had this hardware, laying on the shelf, and I enjoy doing this type of work. This is kind of what I do for a living, primarily. So I enjoy doing this, and it was a fun experiment to rip this down and see how it all works. So, but yes, you can definitely use this on a Tormach. Okay, so let's kind of go through this FPGA code. So we'll start at the top here, and this is the simplest. So this module here is a 4-channel analog input module, and it's just measuring a voltage. It's just like a multimeter, but instead of having a digital display, it reads into the software. So that's what this piece of code is doing here. It's reading basically a multimeter and then allowing that voltage value to pass out. So that's what this bar graph is running on. It's measuring the voltage off of that start pin, and displaying the signal strength. And that's why I had the hardest trouble with this start pin, because they dual purposed it. The start pin not only is an input to start the probe to turn it on and off, but then when it's not being used, it's also an output of an analog voltage. So they not only did they dual purpose it, but they intermixed digital and analog signals. So that's what really threw me for a loop. It took me a couple hours to figure that out. So that's what this is doing. It's just reading the voltage. Now this loop down here, this is where all the bread and butter and magic happens. So this guy here is another hardware interface, and instead of reading an analog voltage, what it's doing is it's reading the digital signal levels coming from the OMM. So that's this center module, okay? And we've got this wired up to this is wired up to this signal 1 and signal 2, and not signal 1. So the yellow and gray wire are connected to that digital input. Okay, so that's that signal coming in. And it's this data that you're seeing on this graph. So as it transitions from high to low through time, that's what you're seeing on this graph. So that's what this is reading. And this bottom piece, this is what's putting data in to generate that graph. Okay, so in this code we saw this. So this is reading the array of data to display on the graph. And down below in the processor, or in the FPGA, this is what's putting that data in the buffer to be read out up top. So again, this piece of code is just strictly there for debugging and diagnostic purposes to figure out what the heck this thing was doing. So this was the first piece of code that was written. Then this top piece of code, this is the actual application itself. So everything that you see up here in the top is the actual application. So we take the digital bit, and then I wrote a receiver UART for that digital bit. And basically what this piece of code does is it looks for a transition edge. So as soon as it sees a transition edge, it starts a timer. And it waits that 1.25 microseconds, I think we said. And then after 1.25 microseconds, it samples that value again. And then it shifts it into this 8-bit number. And then it waits another 8 microseconds. And then it takes another one and shifts it in. And then it does that 8 times until it reads this whole digital pattern. And then once that pattern is read, it outputs that byte. So that's how we're actually reading. It's basically just a clocked shift. And then I also have a counter here to tell me how many items have been received, so that I can trigger when this counter changes. So then we take that 8-bit byte, and then this is the decoding of it. So we look and make sure that the first 2 bytes are 0. So this is our error check. So that's our error flag. And then after that, we make sure that all the other 2 byte pairs are complement of each other. This is a Xor Exclusive OR gate. And then if all of these are true, then we won't have an error. If all these are false, what we'll do is we start a timer, and then we pulse the error for a certain amount of time. That way we make sure that the machine will see the error, and it just doesn't pulse for like a microsecond and go away again. We want that machine to be able to respond and catch the error. The machine may not be reading its digital inputs faster than this, so we always have to give it some time to assert the signal and for the other guy to read it. Then down here is the touch command. So we're just pulling off one of the digital lines because we're checking it here. And then if there is an error, we force the touch, so that we do stop. And then here is the changed flag and the low battery flag. So that's basically decoding the packet. And then this last piece here, basically this is just another timer. And then every time that a new data byte has been received, we store what the last delta time was, so it tells us how much time has elapsed between each packet. And then this here is doing a check to make sure that this timer does not exceed a certain amount, and that's set for 20 milliseconds. So if we don't receive a data packet within 20 milliseconds, this is going to come up and flag an error. So that's another way that we can check for our error. So that is basically, you know, the logic that is being used in software. Now, if you look at an MI12 interface board, there's a lot of circuitry on that board because of, you know, all of this logic is being done with discrete chips. So that's why it's so large. You know, it's a little older style. You know, FPGAs were in their infancy when the MI12 was designed. So that's why it is the way that it is. So the last loop is for the start command, and the start command is kind of tricky. So let's take a look at the circuit board real quick. I took some pictures of the circuit board so that we can look at it a little bit easier. So we can look at it up close. So here's the top side of the circuit board. And again, to Renishaw's credit, they did a wonderful job in, you know, not only laying out their boards, but also manufacturing their boards and then labeling everything. So everything is labeled on not only the wire colors that they're expecting you to use, but also what that pin does. So you've got your ground, your 0 volts, your 10 volts input, your screen, so that's your shield, the start, and then signal and not signal. So that's your 422 data and that's your start data. This orange LED will light up when it's sending a start. These are infrared transmitters that actually pulse out infrared light to turn the probe on. This is a status indication light of if it's receiving a signal, and then this is just a power light. Up here, that guy is the infrared receiver that is used to read the data off of the probe and then process it. Now, I don't know why they put this big shield in here. There really isn't anything that's running at very high frequency or that's going to generate a lot of RF interference. Normally you see this, you know, in computers and computer chips to try to, you know, quiet stuff down and reduce emissions. I think this might just be here for mounting abilities because the faceplate mounts right here. So that's more why I think they did it. These are your configuration switches. So you can set the transmit and receive sensitivity. So if you have a lot of machines in very close proximity that are smaller, you may not want this thing blasting out at full power because it can interfere with other probes and other machines, and that makes for a bad day. So they left these switches on for you so you can adjust the intensity of the transmit and the sensitivity of the receive. And then this little portion of circuitry over here, this is a transistor, and this transistor is what actually fires the infrared transmitters, and then this is a little Mosfet that triggers the transistor to turn on and off. I had to look into this quite a bit. So then here's the back side of the board. So these are the pins for the connectors for the wires to attach. This down here, these are voltage regulators. These are standard LM78L05. So these are 5-volt voltage regulators. So it's taking the 10 volts in and then regulating it down to 5 volts. And then most of the circuitry operates at 5 volts. These are filter caps here for the 10 volts coming in. They're rated at 16 volts, so you don't want to go much over 10. And then these are rated at 6.3 volts. They really cut their voltage ratings close. Typically, I rate capacitors at twice the operating voltage that I'm going to use them at, personally. But so these are 5-volt regulators, so that's generating 5-volt rails. And then this guy is a negative 5 volts, so it will generate the reciprocal of whatever voltage you put into it. So if you put 5 volts in, which is what they're doing, you're going to get minus 5 volts out. And they do that so they have a plus-minus rail for all the op amps that are on here. There's quite a few op amps. So how does that start logic work? Well, it was hard to trace it out because of all the shields on the board. I didn't want to pull the shields off because you got to heat them up quite a bit. This is a multi-layer board as well. And to get the shields off, you run a very high risk of lifting pads on the board. And, you know, I paid $500 for this thing. I didn't want to destroy it. So the start pin is right here. And it does two main paths. One path flows through this resistor, through this leg, through this cap. Okay, now that cap is very important. This is a diode, and then it comes down through here and comes to this MOSFET and then this resistor here. And then from here it goes to the other side of the board to drive the other MOSFET and the transistor. So here's where it gets weird. If you take that start signal and you just ground it, it's normally pulled up. Originally, at face value, it looks like it's pulled up to 5 volts. But it's not. It's an analog output that's representative of the signal strength. So you get confused at first because you read it with the probe off and it reads 4.7 volts, and it's like, oh, okay, it's pulled up. I need to pull it low to start this thing. Well, you pull it low, nothing happens. And the reason for that is this capacitor. So they have a high-pass filter on here where it will only trigger the transmitter when you put a high enough frequency square wave into the start pin. Oh, and by the way, there's no real pull-up that's strong on this start pin. So you actually have to use a totem pole driver that will force 5 volts in and then force the pin to ground. And then that has to run. It started working around 500 hertz, but the waves coming off of the IR transmitter. So I put a scope right here on the gate of this MOSFET here to look at how the transistor was being gated. And they still had a lot of slew to them at 500 hertz, and the slew pretty much started going away at 2 kilohertz. So that's where I ended up running it was 2 kilohertz. So and they do that so that the signal strength analog voltage doesn't accidentally trip the start transmitter, because when the start transmitter goes off, it will interfere with the transmission data from the probe, and you don't want that while the probe's operating. So that's why they did this. And then the second leg comes up over here, comes underneath this cap and wraps around over here. Now this is another diode. Okay, now this diode only goes this way. So this diode allows power to flow into the start pin, and then this diode makes it so the power flows into here. So when you drive that 5 volt signal in to make this logic level transition, it gets stopped by this diode and doesn't come over here, because over here, this is the circuitry that is used to sense how much signal strength the OMM is receiving from the probe, and then generate that appropriate analog voltage that you can read to see what your signal strength actually is. So, that's basically it in a nutshell. And then on the other side of the board, you can kind of peek in and see some of the components here. What basically this is doing is it's just doing a little bit of filtering and thresholding on the IR receiver to try to filter out as much background infrared radiation noise that they can, so that you get a pretty clean signal. It does an okay job, but you definitely can get a lot of interference from this guy, and I can demonstrate that for you in a minute. So what that means is that when you go to start this thing, you need to have a digital line driver that not only can drive a totem pole driver where it will force 5 volts in and then pull the line to ground, but then it also needs an enable-disable line so that it transitions into a high Z state. Now a high Z state just means it's got a lot of resistance, typically a mega ohm or more. And you need that high resistance so then the analog voltage will read out correctly and function correctly. So if you pull that pin to ground, it prevents the receiver side from working. So that's why I had a lot of trouble with this. It only works, the receiver part will only work when the start pin is left in a high Z state. You can't pull it up or you can't pull it down. It's got to be floating. And then the analog input measurement that you use, either a multimeter or in this case the ADD converter that we're using, also has to have a high level of input impedance so it doesn't drag the signal down too bad. So that's what this piece of code is doing down here. So we'll walk through it real quick. We wait to see this start trigger. So that's the start trigger that gets sent from the screen. So when I click this button, basically this goes true and then this loop stops, so then it carries over and runs this code. And then what it does is it starts with the digital output line high, and then it changes the pin direction on that digital line to be an output. So that's what this is doing. It's setting it as an output. So now instead of being high Z stated, we're going to actually start driving the pin. And then this loop here, all it's doing is it's generating that 2 kilohertz square wave and it's driving the pin high, low, high, low, high, low at 2 kilohertz for a finite period. And I'm using about a half a second. It worked down to about a quarter of a second or less, and it works, you know, all the way up. So I chose half a second. You know, it worked good. So then once this loop completes, it sets the output of the digital line back to high, and then it turns it back into an input, which does that high Z state that we need for the OMM to then operate correctly. So then that is the start portion of code. So to get this to work, you need this start portion of code, and you need this upper portion of code, and then if you want to read the signal level, you need an analog input with this portion of code. Now this piece down here, again, this is just for debugging, and this is how I'm sending that receive byte and receive time to these graphs. So that's how these graphs are being generated. That's just this little bit of extra logic. Okay. Now I said earlier I might transition this over to maybe a PIC chip. I thought about Arduino or a Raspberry Pi. I don't have a lot of experience with either one of those platforms. I used an Arduino a little bit. I think you would have to get into the lower level layer of coding to be able to get this to work because of the very stringent timing requirements that are needed. I think I can be successful at getting a PIC chip to work using the hardware input capture lines to generate clock counts of when it sees the data lines transition and when it doesn't see, and then from that data you can decode it. The Fpga works really well because all of this code inside this loop right here, this code is executing at 40 megahertz. So it is, you know, that's a 25 nanosecond, you know, loop rate. And seeing how we're only measuring a 1 microsecond time, you know, we've got about 40 clock cycles per 1 microsecond. So this will not miss any edges, and it's a very good way to do these UARTs and computations. That's why FPGAs are so powerful. So getting this into a PIC chip, you can't, I don't know if you'll be able to do a software loop fast enough, even a PIC chip in assembly, to be able to reliably read this. You're going to have to use some portion of hardware on the chip, like the input capture port, to be able to do this inside of a PIC. You should be able to do that with an Arduino or a Raspberry Pi as well. I just haven't done it personally. So that's about it for the OMM. So you can see that we've got the OMM working. It does everything that the MI12 device that you would buy does, and I was able to save myself $500 at the cost of about 5 or 6 hours. So if you count my time, I probably broke even. If you count the hardware, this method is way more expensive, but I had it sitting on the desk, and you know, might as well put it to use. So with that, either I'm, you know, way blew you away, or you know, feel free to ask any questions, and we can do some question and answers. If you want to see anything a little bit more closely or explained, let me know. I think we're on about a 30-second delay for the comments, so bear with me if you get some dead time. And if you guys want to talk about anything else, you know, feel free as well. I've got the tool setter here as well. So like I said in the beginning, these tool setters are really simple to read. They're just a dry contact. It's just 2 wires. So you just feed that into a digital input, you do some debouncing on it, and you're good to go. You know, that's the tool setter. So the tool setter's, you know, cake simple. It's the optical interface that was the hard part. And again, this tool setter was gifted to us by a very, very generous viewer. So I thank them a lot every time. I always want to make sure everybody knows that, you know, this was a gift. So that's a very, very appreciated gift. the probe and the OMM, you know, we purchased. So everyone's quiet tonight, kind of like deer in the headlights syndrome. Hello from Brazil. Nice. Hello, Herberto. Sorry I missed you on the jumping on the comments there. The MI5, I think that MI5 is a little bit older interface, but yeah, and use an MP3 probe. Yeah, I think that's a little bit older stuff. How does this get integrated in the control? Then do you need probing routines? Good question, Jason. So how does this get integrated into the control? Unfortunately, that is a very machine specific question. So I can answer your question in relation to Fidel and how Fidel does things, and then I also have a little bit of background on how some of the other machines do it. Basically, every machine has a input to trigger a probe setting, and there's certain G codes that you use to tell the machine to move while monitoring the probe signal, and then the machine will stop moving even if it's not at its target if the probe triggers. So every machine has that. Now when you buy these probes from Renishaw, they will ask you what machine you have, and then Renishaw has a library of macros that can run on the machine. Because being able to probe and move the machine and then stop the machine isn't just enough. If you want to find the center of a circle, you need to tell the machine to move the probe to at least 3 points and take 3 measurements, and then you need to do some trig to figure out where the center of that circle is. Or if you want to figure out, like, if there is a degree slant in a part, like if you don't square your vise and you want to use the rotation comp in the machine, you have to probe at least 2 points along that edge to then figure out the rotation of the part to comp out the rotation. So the answer is every machine has an input. Every machine should also have M codes to trigger the start signal and trigger the selective if you want the spindle probe or the tool setter. And then there's macros that need to run in the machine to perform the math operations to get the final answer of being able to set your work offset. Like if you wanted to set a work offset at the center of a hole, you would need a macro that would probe at least 3 points, figure out where that center is, and then go, modify your work offset appropriately so that then your work offset will be, correct to the part. So that's the long-winded answer to that. Oh, okay, Josh. So I think Jason's question just answered Josh's question. So pretty much, I'm going to do a video, and I'm going to do an installation video. I'm not going to do a live stream. I'll do a real installation video on how to wire all this up, complete with schematics and everything. So Fidel already has some canned built-in probing routines. I'm going to probably write some probing routines as well, because the Fidel probing routines does not look at the error signal at all. So it would be nice to know if it's actually a real probe touch or if it's an error. And then I don't know if the probing routines have the selector in there or not for the tool setter or the probe. So I'm going to look at that. But basically, you wire in the probe output into the machine. You need to wire a start command, a select command, and then you can wire in the error line. So it's only four bits that have to be wired in and out of the machine. It's pretty easy. Yes, Renishaw has their own macros that they like to use. Good morning, Benny, or good evening, depending on where you are in the world. Yeah, if you call Renishaw, they should be able to provide you their macros based on your machine type. If you buy the probe used, I don't know what their policy is about providing the macros to you if you purchase second-hand hardware, but if you buy brand new hardware and have it installed, I'm pretty sure the macros come as part of the package. I don't quote me on that. I don't know for sure, but yes, Renishaw has a whole bunch of macros. Okay, so G says sometimes you have to provide the serial number of your hardware. That might be to make sure that it didn't fall off the back of a truck. Yeah, I mean, the macros aren't horribly difficult if you're familiar with programming macros and you're familiar with the trigonometry. It's basically just a lot of variable manipulation in the machine. Fidel variables are V words, and I believe there's 100 of them. So you can store the points in the V words, and then you can do the trigonometry on those V points. So I think Fidel can do sine, cosine, tangent, square root. You basically just write the math out, and then you plug and chug into the work offsets. So it's not horribly difficult to do, but if you can get the macros from Renishaw, it will save you a lot of legwork. So I might actually contact them, and see if I can get the macros myself. So for Fidel, see if they have anything for Fidel. Oh, okay. Yeah. Did Centroid have their own probe? I don't know if they did or not. I know Tormach, they sell their own probing system, but I don't think it's nearly as accurate as a Renishaw. The Renishaws are repeatable within, I think it's 40 millionths. I think it's 1 micron. Ah, yes, yes. That is a good question. Hold on 1 second. Let me. Let me just disconnect you real quick. All right, so the question is, does the probe need to be swept in like a hamar? And the answer is yes. And if you look right here, here, there's 4 of them, and here, that is what allows you to adjust the center of the probe relative to the spindle. Okay, so if the probe has a little bit of kick to it, you can adjust it out so that the probe tip is in the very, very center of the rotation. Okay. Now, one thing to keep in mind is anytime you change your probe tip, your next probe, might be a little bit off relative to this probe. So you have to go through the centering procedure anytime you change the probe tip at all, or anytime you adjust anything in here, you need to recenter it. Very good question, Josh. Okay, I'm not familiar with Accurite or anything. The Centroid has their own, but they really like it money. Well, these Renishaw is not cheap. That the OMM, I'm actually a little disappointed. I paid $500 for it. I mean, it probably would take me a couple of weeks, but I could re-engineer the OMM pretty easily as well. Yeah, getting your probe aligned is very critical. The other thing that you want to do when you install a probe on a CNC machine, you really want to try to get yourself a ring gauge or some, you know, larger part that's a couple of inches that is of very accurate and known dimensions, and then put that on your table. And then what a lot of the probe softwares will do is they will approach the part and they will probe that, and you can do a calibration routine, and then for each cardinal direction, like coming in X positive or coming in X negative or Y positive, Y negative, or, you know, Z negative, it will allow you to put a little bit of offset routine in there to compensate for any inaccuracies in the probe and backlash. So you can get very, very accurate probing results, you know, even on a machine that might not be the best. Yep, master ring gauge. Josh, I second your comments. So you're surprised at how expensive the OMM is for how simple it is. Yeah, I agree. I mean, you know that. Let's pull up that circuit board again. So, you know, this circuit board, mass produced. I don't know. Even let's not even say mass produced. Let's just say produced in moderate quantities. You know, I don't know, maybe $50. Call it, maybe. I mean, there's not that much on there. Most of it's all analog, you know, components. There's not much on it. So call it $100. You know, and then to machine the housing, you know, I mean, you know, I mean, there's a lot of machinists in the room. How long would it take you to machine that, you know, in a production environment? You know, I'm seeing maybe, I don't know, $200 worth of actual stuff here. So yeah, I'm surprised at how expensive it is. And yes, you have to pay for the R&D time and the support time and all of that stuff. But I mean, there's one of these on almost every single CNC machine there is in industry. So I mean, they sell a lot of them. Yeah, I'm surprised at how expensive they are too. But people pay it. They're getting it. Can't argue with that. So, okay, well, I'll give a couple more minutes for any other questions if you guys have it, and then we'll finish this one up. I think it was fun. You know, it was cool. It was neat to dive into this thing and, you know, see how the nuts and bolts and guts of it work. And it's cool that I've got a MI12 replacement working. So pretty soon, probably within the next couple of weeks, you guys should see a video pop up for how to install a probe on a Fidel. I don't think it's 2 minutes of spindle time. That's some pretty heavy hogging if you get that hogged out in 2 minutes. We could calculate out the volume and see how long. You got a couple of tapped holes there too. So if you're only on a 3-axis if you're only on a 3-axis machine, you've got at least 3 operations there. So I don't think it's a couple minutes, but yeah. Yeah, I agree. I agree, Jason. Oh, hey Peter. Good evening. Yeah, don't worry about missing the beginning. I'm gonna. You can watch the whole thing. Oh. Yeah, I'll make this live stream public so it can be searchable and everything. It was good information. How's the rebuilt spindle motor? I knew somebody was going to ask about that. The rebuilt spindle motor is pretty good. I'm happy with the results. I did a job where I was drilling a whole bunch of very small holes, so I had it running at 7,500 RPM for a couple of hours, and it runs remarkably smoother. It still has a little bit of vibration in it. I can't tell if that vibration is from the commutation of the spindle drive running at that high frequency, or if it's actual real physical vibration, or if it's coming from the spindle. But it does still have a little tiny bit of vibration, but at least now it doesn't sound like you want to run for your life. So in the end, spindle motor's good. You know, I can run up at 7,500 RPM now without thinking twice. I was limiting my spindle down at 5,000 RPM just because anything above that got real scary. So yeah, it's much better. Yeah, and I edited and uploaded that video a while ago. I just didn't release it yet. And I did that video before I saw Brian's video, B Block, and I kind of felt like a wimp for making my video and being so self-conscious that I kind of oopsed and, you know, set the motor down a little hard. Yeah. Then I saw his video and my heart sunk. I just feel horrible. Ah, Dylan, yeah, trying to find information on a Mitsubishi. Yeah, that was one of the reasons why I bought Fidel. You know, the information is very readily out there, and there's a lot of people that are using Fidels. You know, they're basically like, you know, Chevys. There's just a ton of them out there. There's a ton of parts out there, and there's a ton of manuals. No, the motor wouldn't have hit my toes. We're good. Don't put your toes under it. Besides, if the motor fell off the spindle column like that, I would be more worried about cracking my table and a lot of other things. Yeah, I don't have any experience with any of the Mitsubishi controllers at all, so I wouldn't be able to add anything to that. Well, you know, it's my garage. Oh, hold on a second, Josh. I'll find it for you. Oh, maybe it's BB block. Hold on, I got it here somewhere. Yeah, there's the video. I watched that and I saw the title from it and I was like, oh no. And unfortunately, the title was very correct. And I cringed, my heart sunk. Oh, cool. That'd be cool, G. They're not bad machines, you know. Just watch out, you know. They're older, and watch the wears. Dylan, if you want, send me an email. I can help you out with post processors. Actually, I think I did a post processor for a gentleman that had a Mitsubishi, or maybe it was a Viper or something. So, yeah, just send me an email. I don't do the post processor mods for free, but I'm pretty cheap. 3016, I think, is a linear machine, G, just so you know. Yeah, a lot of the rigid tap cycles don't work in a lot of the fusion posts. I'm actually working on with one of the guys at Autodesk to get the Fidel post fixed up, and it looks a lot better. I've been doing some testing on it. Yep, that's typical. And you know, so with a lot of machines, the rigid tapping is an option for the machine, and you know, Autodesk wants the post processor to be compatible with the most amount of machines as possible. So if the majority of machines don't have rigid tapping, or if it's an option, all machines will do non-rigid tapping, but only a few will do rigid tapping, so they support non-rigid tapping first. Oh, I didn't know you had two Fidels. That's cool. Oh, Peter, you're still having problems with rigid tapping? Yeah, that's typical. A lot of the machines will have a preparatory cycle that you have to run through to synchronize the spindle with the Z column or the Z axes. And then, you know, you have to describe the thread pitch in some format. You know, every machine is a little tiny bit different. Yeah, I had another viewer help me out, get a whole complete set of circuit cards for my machine. So you're probably going to see a Fidel controller upgrade video soon as well. We're going to go from -4 cards to -5 cards. So I'm pretty pumped and excited about that. Yeah, 4020s are nice machines. That's a good mid-size Fidel machine. You just got to watch out for the boxway wear and make sure the gibs aren't wearing out. Oh, that stinks, Peter. I hope you can get it worked out. Rigid tapping is awesome. You know, especially if you do parts with a lot of holes in them. Um, the dive light has tons and tons of 440 tapped holes all over it. Ooh, high torque. Nice. I think that has a 15 horsepower continuous, I believe. 10,000 RPM. Cool. All right, folks. Well, I think I'm going to wrap it up at 11:30. So if you have any other questions on the OMM or anything else, you know, type it in now, and else we'll call it a night. I've heard about a 4020 linear machine, but I've never actually seen or known anybody that has seen it in person. It's like a mythical unicorn. I don't know if I would want a 4020 in linear, though. That's a fairly large machine. If you did that as a linear machine, I think you would want multiple linears. If it is made, I think it only would have 2 rails still. Ouch, Dylan. That hurts. Yeah, have a good evening, Jason. Thanks for sticking around and hanging out with us. Okay, folks, so I'm going to wrap it up. Thanks for joining us for the live stream, and thanks for sticking around while we went over the OMM, and we'll see you on the next video. Have a good night.